So in the last session, we were discussing the Naive-Bayes algorithm, which is purely based on probability. This is purely based on probability. Conditional probability is the fundamental for this. And Bayesian algorithm or Bayesian condition probability is what Naive-Bayes uses. It uses the probability of an event. It calculates the probability of event based on the occurrence of another event. Once another event has happened, then it will calculate the probability of the next event or what will happen if the other event, what is the impact of the other event's occurrence on this current event. That is what conditional probability is all about. Now, in this case where we were calculating the probability of the car being stolen, if it is yellow, SUV and domestic. If the car is yellow, SUV and domestic, what is the probability and what is the class? Will that be stolen? Yes or no? So for that, we need to calculate probability of yes given yellow, SUV and domestic, probability of no given yellow, SUV and domestic. Whichever has the highest probability, that will be the predicted class. So for calculating probability as given yellow, SUV and domestic, we have to calculate the three conditional probability of yellow given S, probability of SUV given S, probability of domestic given S. Then we multiply these three, then we get the likelihood of evidence. Then we take the prior probability of yes, which is 5 yeses and 5 no's are there. 5 by 10, you'll get 0.5, and then you multiply the likelihood of evidence with the prior probability, you will get the final probability of that. Probability of S given yellow, SUV and domestic. Now, why we are only calculating numerator? Because for both the calculations, denominator is same. Denominator is probability of yellow multiplied by probability of SUV multiplied by probability of domestic. The denominator is common for both the calculations. So, no point in calculating because the effect will be similar. So, we are calculating the numerator here. Probability of no, and then we find out the probability of no is the highest. So, the final probability will be no, the car will not be stolen if it is yellow color, SUV, and if it is domestic origin. The car will not be stolen. So that is the reason. So the algorithm will initially calculate these probability tables and store them in the memory. Naive-Bayes is slightly different. It once you give the data to the algorithm, first it will create the cross tabulations like this, and then it will calculate the probabilities and it will store them in the memory. As and when you give a predictive case for it, so it uses the calculated probabilities and calculates the final conditional probability. So this is slightly different in terms of the other calculations. So here, first, all the probabilities will be calculated and stored in the memory. So when you want to see the output, you can see the probability tables also. So the probabilities will all be calculated and then it will be. So any doubts in this calculation? Okay, now the next other calculation also you can see here. So here we are being asked to calculate the probability that the fruit is banana if it is long, sweet and yellow. Find the probability the fruit type is banana if it is long, sweet and yellow. So we have to calculate, we have three types of fruits, banana, orange and other. So we have to calculate three probabilities. So the first one is probability that the fruit is banana given if it is long. We also need to calculate probability of the fruit being orange if it is long, sweet and yellow. We also need to calculate the probability of the fruit being other if it is long, sweet and yellow. So these three probabilities we have to calculate and then we will get the probability of what is if the fruit is long, sweet and yellow, it is banana or not. Okay. So three probabilities have to be calculated. So for the first probability, what we have to calculate? We have to calculate probability of banana given it is. Similarly, we also have to calculate probability of banana given it is. We also have to calculate probability of banana given it is. Then we multiply this, we get the likelihood of evidence. You get the likelihood of evidence. Oh, sorry. I have written it reverse. So once we get the final, the x1 is equal to long, three independent variables are there. Long, sweet, and there are three independent variables are there. Our dependent variable is multinomial. That means there are more than two. So in this case, the dependent variable is multinomial. It's not a binary problem. It is a multinomial problem. because there are more than 2 levels in our dependent variable. So how many long end bananas are there? Is equal to 400 divided by 400 longs are there, right? Total amount of total longs are 400 by 500. How many sweet end bananas are there? 350 divided by sweet is 650, na? Total of sweet is 0.53. How many yellow are banana? 450 by 800. So likelihood of evidence is 0.8 multiplied by this multiplied by 0.242308. Now we also have to calculate the prior probabilities. So prior probability y is equal to banana, y is equal to orange, and y is equal to other. So how many bananas are there? Is equal to 500 by 1000. Total number of bananas is 500 by how many others are there? Now the prior probability of banana is this. If you multiply the evidence, prior probability, you got 0.121154. Oh, we got something wrong here. Hey, total number of bananas are 500 only. Yeah. It's not 650, it is 500. This also, because we have only 500 bananas, right? Total sample of bananas is, so we have calculated the first one, 0.252. Similarly, we have to do the other calculations. So we will replace banana with orange. Long and orange, so is equal to 0 by, this is a problem because if there is 1 0 in the probability calculations, the whole probability will become. So this is where we have something called Laplace correction. This is again common interview question. Laplace is assigning, replacing probability 0, a value closer to 0.05. This we call it as Laplace correction. When your probability is 0, we will replace it with a smaller value which is closer to 0. That we call it as Laplace correction. So since this is becoming 0, we will replace it with 0.05. Some probable value which is closer to 0. So how many sweet and orange? Sweet and orange are 150 by 300. 150 divided by 300. How many yellow and orange? 300 by, so is equal to this into this into this. The prior probability of orange is 0.3. So if you multiply this, you get 0.075. This is your Laplace correction. Similarly, we also have to calculate the other part, which is calculated here. So how many long and other? Long and other is 100 by 200. 150 by 200. Yellow and other 50 by 200. Likelihood of evidence, multiply this. Prior probability of other 0.2. The final probability is 0.0975 into 0.2, 0.018. So this would be, so the probability is higher, largest probability. So most probably, if the fruit is long, sweet and yellow, it has the highest probability. So naive Bayes is very interesting one. Email spam, initial algorithm where Google used for spam prediction was naive Bayes. Now Google is using deep learning and other advanced algorithms, but the initial algorithm which was preferred for spam classification was sentiment analysis that we do in text mining is again based on naive Bayes. So naive Bayes is widely used in text mining and in multinomial problems also. Naive Bayes has a slightly good, it's a base algorithm in multinomial problems. Binary logistic regression is only a binary problem. There is a multinomial logistic regression. There is also something called multinomial logistic regression is also there, but its performance is not as good compared to the naive Bayes. So in case of multinomial problems, naive Bayes is treated as the base algorithm. In case of multinomial problems, naive Bayes is treated as a base algorithm. Now, decision tree, random forest, gradient boosting, all work as binary classifications, also work as multinomial classification algorithms. So the tree-based models will work both on binary data and multinomial data. Tree-based algorithms will work both as binary algorithm as well as multinomial algorithm. They have slightly better performance than naive Bayes. They have slightly better performance than. So naive Bayes as a multinomial algorithm is a better. So meanwhile, you can go to driven data and download the vaccine prediction data. we will work on that vaccine prediction. Driven data, web page is driven, website is driven data. You are able to get the calculations, or should I write them on the side also? So import the train file, test file, and the labels file. All right, all of you have imported train, test, and all of you got the data files. Now, whoever imported, please run the info and see if there are missing values. Features are the independent variables. Because two dependent variables are there, they are given a separate file. So you have to build one model with the same independent variables for predicting seasonal flu, the other with H1N1. So two models have to build. If you want to submit the predictions, you have to build two models and then copy paste the predictions into sample submission file and upload into the competition site. You will get the score. So vaccine train dot info. So the data size is 26,707. And we have missing values. In fact, many missing values are there in many columns, many variables. Test also, I think, same case. So all of you inputted the data. So there are many missing values here. Dot info. Again, test also has many missing values. There are no numeric variables. All of them are categorical only. All the variables are categorical. No, why do you need to do? So we put a statement on top. No, 0 means no, 1 means yes, until unless specified. Rather than changing everything, you put a statement on top saying that 0 represents no, 1 represents yes, until unless specified. So that's what they use here now. Here also they say the same thing. See here, for all binary variables, 0 is equal to no, 1 is equal to yes. You just put it. That is different. So that's what now. They specify it as, they specified it very clearly. For binary variables only, 0 and 1 means no and yes. For multinomial, you have to look at the things. So you can copy this statement into the box. Don't change them. Changing again is a problem. Ultimately, we want the data back in the categorical format only, right? So better to copy the statement and put them in a cell somewhere where what the reference means. So all those problems unnecessarily, why to waste time on that? So we will focus more on the model building part and the, okay. So you copy the, from the data dictionary, you can copy and paste the, what that 0 means, what 1 means and all, and paste it there. That would be the best option. Now, till now, we were doing manual imputation. Today, we will do mice imputation in Python. Mice multivariate imputation by chained equations is the full form of mice. Now, imputation of missing values, they made it a separate category in Python. We have in sklearn only. So for univariate, we use simple imputer. Simple imputer is like what we do manually. Mean, median, and most frequent. Strategy is equal to mean, median, or most frequent. Univariate. Univariate means single column. Now, in multivariate, we have this iterative imputer. What you call, so mice algorithm is used in iterative imputer. So it is still in the experimental phase. So at each step, a feature column is designated as dependent variable. So whichever is the missing variable, that column will become dependent variable. Rest of all will become independent variables. And a regressor will be fit on X and Y. Right. Once you fit the regressor, you get the predicted values, right? Predicted probabilities and predicted values and classes. Accordingly, we will do the replacement of the missing values. So that is what mice will do. Iterative imputer. Iterative imputer is a very, very powerful, which is widely used in industry for doing missing value imputations. If you don't want to do manual or univariate imputations, you want to take the other variables impact on the missing value and then do the imputation, you have to use the algorithm. The algorithm which is mostly used is, and in Python, we call it as iterative imputer. Okay. So iterative imputer, estimator is there. So estimator, Bayesian ridge is the default algorithm that is used for imputation. We can also use other estimators. Okay. So we will be using this sklearn.impute. Now let us combine the DF. For imputation purposes, we will combine both the data frames. So here we don't have the dependent variable is already separate. So we have to add what you call train and test as additional columns, and then we have to impute. Or we can do what you call row wise in what you call 26,707. Okay, no need. We will use vaccine train square bracket data is equal to square bracket data is equal to So in both the data frames, I am creating a common column called data. And in train, filling it up with the word train, and in test, filling it with the word test. Combined df is equal to pd dot concat vaccine train, comma, vaccine test, comma, axis is equal to 0. Row-wise concatenation. So, so that we'll know what data is what. We have combined them, right? You can do row-wise concatenation also, and then you can separate them based on the rows, but it's better to do what we call separation using train and test condition. Now we have to do label encoding. But when you're label encoding, we need to keep the missing values as, we should not change that part. Okay, keeping the missing values as missing only. Rest of the data has to be label encoded. So just check on Stack Overflow from sklearn.preprocessing label encoder. All right, first we have the missing values. So I think we can use this. So we have a simple code available. Let us try this one. Before that, let us confirm the missing values, whether how many missing values we have. Okay, we can do the combined df dot info 53,415. Data size is 53,415. And we can see the missing values, which wherever it is less than 53,415, we will take it as 53,000. So what is suggested in this code is, which we are going to experiment this thing is, first he is asking us to create a original data frame. So original is equal to combine df. This is our data frame. Then he has created a mask data frame. Combine df underscore 1 is null. Combine df dot is null. Combine df, yeah, we see the missing values are still there, right? And rest of them has been converted into numbers. Now rest of them has been converted into numbers. So what technically we are doing here is, we are is null. Is null will give true and false, right? Wherever there is a missing value, it will put true. Wherever there is no missing value, it will take it as false. Now we have combined df, we have converted the whole data frame into a string, and then we applied the label encoder, like how we do on a normal data. Then we have used the where function. Where is like if statement. Where is equivalent to if statement, equivalent to mask or original. If it is equivalent to mask, it will take the true value and replace it with null, and original will be kept as, yeah, by default on the empty cell, NaN is installed, so inputted. NaN is imputed in place of empty cell. Not neutral, it is a missing value. 1 second, let me move this down so that you can see the label encoder. Do the imputation process. No, it is showing, right? No, you have to assign combined df is equal to. I forgot. Now we didn't give the name. So we didn't give the name, right? For the mask, I forgot to give the name. So combined df is equal to combined df. Then I did the info again. You can see here the missing values are as it is. I forgot to give the name. Combined df is equal to, for the mask command, where command you have to give the combined df name. From sklearn.experimental enable iterative imputer. From sklearn.impute iterative imputer. So we have to enable the iterative imputer, then we'll impute it. So I am going to use, by default, it is using Bayesian ridge. We are not going to use Bayesian ridge. Ridge is a what we call lasso ridge. We will study when we talk about regularization techniques. They are preferably used on numerical data. But our data is mostly categorical in nature. So we are using decision tree classifier as our estimator or the algorithm for imputation. The algorithm that we are going to use is decision tree classifier for imputational purposes. So fit underscore transform is there. Imputer is equal to iterative imputer. Estimator is equal to decision tree classifier. Initial strategy is equal to most underscore frequent. Max iter is equal to 10. So we are going with 10 iterations. Decision tree classifier. Now we need to drop combined df is equal to combined df dot drop respondent underscore id. Let us say combined df1 is equal to, and then data comma axis is equal to 1. So ID column and the data column we are doing, I am taking it as combined df1. Combined df1 is equal to combined df dot drop respondent ID and data. 2 columns which are not needed for imputational purposes, right? Rename your data frame, combine DF1, because we want data back. That is what we are going to use for splitting the data into train and test. So we'll add that column later, but for the time being, for imputation, we are going to combine DF1 underscore impute is equal to imputer dot fit combine DF1 dot apply imputer dot fit underscore transform. 2D array. So we can't give like this. Imputer dot fit underscore transform combine DF1. So initially mode will be used for replacement and then it will do the imputation. It has already done. Let us see if it worked or not. So combine DF1 dot underscore impute is equal to PD dot data frame combine DF1 underscore impute comma columns is equal to combine DF1 dot columns combine DF1 underscore impute dot info. See, all of them have been, there are no missing values. All of them have been imputed. This is the process of mice algorithm in Python. Okay, first you need to label and code. In this case, we have all object columns. So we did the complete data frame. But if you have both numeric and object, you separate the numeric calls and object calls. Run the label encoder only on object calls, keeping the missing values as it is. Let the numeric calls have missing values as it is. Combine them back into single data frame and then run the imputer. Okay. So you can do two things. On numerical data, you can do a regression based imputer. On object calls, you can do a classification based imputer and then you can combine them if you want to do it separately. So regressor for numerical data, classifier for object data. Run it 2 times. It will not take much time. Only thing is keep the iterations. Okay. So this gave us convergence warning. So we would have given more iterations. So we got a convergence warning. So early thing means you have to increase the iteration. Okay. So you can give 20 iterations, not more than that, because it will take time. If you give hundreds of iterations, it will take time. Okay. So once you have this imputer, which is equivalent to mice in R, it's very easy to implement in R. Now it has been implemented in Python also. All right, got this, all of you? All of you got the imputer, this thing combined? Because once the imputer runs, we get a NumPy array. We have to convert it into data frame. But because once you run the fit underscore transform, it will convert it into NumPy arrays. So we have to convert them back to data frame. Run for you, all of you. What it has done, let us see. For there were more employment occupation, there were a lot of missing values, right? Combined DF employment occupation dot value underscore count drop NA is equal to false dot plot kind is equal to bar. See, there are a lot of missing values and different things are there in the employment occupation, right? Most of them are none. So you can see, right, in the employment occupation, more than half of the data is combined DF underscore impute dot employment occupation dot value counts drop NA is equal to false dot plot kind is equal to bar. Now it has allocated, see, there are no missing values and employment occupation 2, 14, 12, 8 it has, and it has allocated according to to all classes it has allocated. Look at it has allocated to all classes. So it used decision tree based classification predictions for imputational purposes. So this is what it has done. This is mice. Iterative. So multivariate imputation using chained equations. Multivariate imputations using chained equations. So the missing variable column will become the dependent variable. Rest of all will become independent variables. In each iteration, the dependent variable will change. The independent variable that has the missing values will become the dependent variable. And then algorithm will run, predictions will be done, and the prediction values will be replaced in the missing value. In the second iteration, the other column which has missing values will become the dependent variable. So like that, it will do the process till all the missing values are. Now, as you can see here, it has done imputation based on the algorithm based prediction, right? And you can see here, the bar plot looks like a stable bar plot rather than this one looks like a highly skewed bar plot. NaN is very high. Now there are no NaNs in our data. There are no NaNs in our data, or missing values are not there. It has allocated missing values with 2, 14, 12 and all the categories based on the predictions generated by decision tree classifier. Now you can use random forest, you can use gradient boosting also. Okay. See, like I told you, tree-based models have good predictive probability. They are used in missing value imputations frequently, right? That is why I am using tree-based models. If you want, you can use logistic regression also. But logistic regression has a problem. We have multinomial classes and binary classes. Logistic regression will either work as binary algorithm, will either work as only multinomial algorithm. It cannot be both. Whereas tree-based algorithms will both identify the dependent variable, will do the both multinomial as well as binary missing value imputation. So tree-based models are preferred. If you have good computing power, random forest is also good imputational. Like I told you, no? Tree-based models are used for imputations, missing value imputations. Tree-based models have good performance. So this is the process of using an algorithm-based imputation method. An algorithm-based imputation method. Manually, what we would have done, we would have taken the most frequent and replaced it with the most frequent, and we would have created a bias. Rather than that, now the allocation based on the algorithm looks like a stable allocation. It has taken consideration of other independent variable impact on the dependent variable, and then it does the imputation. So this is how we have to do nice or iterative input. Limitation C, it is not 100% accurate. There will be some error in this method also. The only thing is, rather than blindly doing a manual imputation, we are doing a statistical imputation here. We are using a statistical method, right? Rather than creating a bias by using mode, or rather than using most frequent or mean median, we are using a statistical model to predict, and prediction based on that model will be taken into the missing value. Now, all models are not 100% accurate, and there will be error in this also. But the error will be moderated. Error will be not in one single location. Error will be spread on all. Sometimes you have to spread your bets. You know, you all know English Premier League, right? So that UK-based football league, one of the highly betted competition in the world. Now, every season, all bet sites will offer you who will win the EPL. Can you make a single team prediction? Some people say Manchester City, Liverpool, their favorite thing, they'll blindly bet on that. But if you are a wise bettor, you will bet on all the teams, weighted average betting you will do. Okay, I'll put 50% of money on Liverpool, 30% on Arsenal, 20% on Manchester City. So that if other one or the other wins, I will be on a safer side. I can moderate and I can still make some money. Now I can do a single team betting. That's a what you call 100%. If you will get a very good. If you are 100% accurate, you will get less return. When you spread your bet like this, you will get less return. But you are on a same thing here also. We are spreading the error or the variables. We can have a model stability. Okay, rather than having one completely dependent upon, we will be spreading the error. It's a safe side. It's still not 100% accurate. Nothing is 100% in machine learning and data science. Like I've been telling you from day one, right? There is nothing called 100%. We can only say 95% confidence levels. But in ML, we go with 0.70 accuracy also as a good. So it's 11 o'clock. You guys will take a break and then we'll come back and build models. Right? Now our data is imputed. Now we are in a position to split the data back to train and test. But before that, we need to add to the combined DF input, square bracket single quote, data is equal to combined DF dot data. So we got an error. I think re-indexing issues. Combined DF underscore input is equal to combined DF dot data dot reset underscore index. Okay. So combined DF underscore input square bracket single quote data is equal to combined DF dot data. So we have resetted the index and we have added the data column back to the train DF is equal to combined DF underscore input square bracket combined DF underscore input dot data double equals to test DF is equal to combined DF one input square bracket combined DF input dot data double equals to test print vaccine train DF dot test DF dot 0. What happened there? We dropped it, right? Then how did it come into our label encoding? Combined DF1 input doesn't have data. Somehow it got changed to 1 and 0. Double equals to 1, double equals to 0. Train is 26707, test is 26708. You have to reset the index. Oh, index column is also added. So we have initially how many variables? So if you drop to the respondent ID, we have dropped, right? So we have to drop 2 more columns and you get 35. Yeah. So first we will use seasonal vaccine. Seasonal vaccine, Y is equal to vaccine labels dot seasonal vaccine, X is equal to vaccine train DF. Now plot the Y. Is it balanced or imbalanced? Bar plot of Y. Oh, we have not label encoded, or is it label? Just do the bar plot of Y. So Y dot plot kind is equal to value counts. Y dot value dot plot kind is equal to, it is in 0 and 1 only, right? 0 and 1. Okay. Now build logistic regression model on seasonal vaccine, build the logistic regression. All right. All of you got the steps. So this is the balanced data. See, 0 and 1 almost all similar. 1 is very few. Hardly 5,000 ones are there. 21,000. This is an imbalanced data. This is balanced data, almost similar. 12,000 and 14,000. Right? This is imbalance. sklearn dot linear underscore model logistic regression. Logit is equal to logistic regression. Logit model is equal to logit x comma y. So iterations needed. Max underscore is equal to 1,000. Logit model dot score x comma y. 77.32. Accuracy of 77 point. Logit predict is equal to logit model dot predict. We will also print the classification report. We will do the AUC curve also. Okay. Classification report y comma logit predict. See, all the metrics are closer to one another for balanced data. But when you look at imbalanced data, you will see a lot of change here. These things will change. Minority class, no? 1. There will be problem. But this is a balanced data. So you can see all the metrics are closer to one another. Similarly, also ROC curve dot display dot from estimator logit comma x comma y. So we got the AUC of 0.84, area under the curve of 0. So looks like a stable model. Looks like a stable model. Primary is accuracy. Okay. Primary is accuracy. First of all, you always look at accuracy of the model. Once you have printed the, then you look at the balance. Imbalanced data situation comes, then you have to look for precision F1 and recall. If it is a balanced data, you don't need to look at precision F1 recall because they will be stable. You can directly go into AUC. Accuracy plus AUC should be between 0.70 and 0.95. Both the metrics, if they are between 0.70 and 0.95, you have a very good model. You might get that scenario. When accuracy is 0.60 or something like it, underfitting closely, then you might have AUC above that metric. But primary accuracy has to meet the criteria of 0.70. First and foremost metric is accuracy. If that meets the criteria of 0.70 above, then only you go and plot the AUC curve. Otherwise, we will not do the other metrics. We'll go to the next level of models, or we will change the data variables. We do variable selection or feature selection. Now, for the convenience sake, let us also logit h1n1 is equal to logit dot fit x comma vaccine labels dot h1n1 vaccine. Logit h1n1 dot score x comma this is equal to logit h1n1 dot predict print classification report labels dot h1n1 vaccine comma logit h1n1 predict. Good. But look at the minority class. Very, very bad. Precision recall and F1 score. Overall accuracy 0.83. But look at the minority class predictions. They are very, very bad. It says like this. Acha. So 0.83. ASC is also 0.83. Now, logit model dot predict is equal to logit h1n1 pd dot data frame logit season dot 2 underscore csv logit underscore season dot csv pd dot data frame dot 2 underscore csv h1 dot csv. Now, slightly there has to be a small change here. Where is the so open the sample submission file. So it is asking for probability predictions. So we have to do slight changes here. Predict underscore proba. No predict underscore proba. So here we have to give probabilities. predicted probabilities. So we have done the predictions, Microsoft Excel. We got the probabilities of both 0 and 1. Okay. So we will take the maximum. So we'll reduce the decimal also. This is H1N1, right? Has to be here. Next, we will open the season 5. Okay, we got the same values. How did we get the same values? We got two probabilities. So we need single probability. If we go to the problem, log proba, what we are getting, let me check. It should accept 1 and 0 also. So we have predicted the probability, we have to take probability for 1, because whether the vaccine, whether the person is taking the vaccine, yes, is the area of focus. That's why we are taking the probabilities for, okay. So that we have copy pasted into the probability submission sheet, and then we have uploaded in the competition site. Okay. So on this data, we can do decision tree or any classification we can build. You can try if you build a model, or in the next session anyway, we'll try to build a model. We'll also have to build the naive-Bayes. So there are different types of naive-Bayes, I told you, right? So naive-Bayes, so you have this one. Gaussian naive-Bayes, multinomial, complement, categorical naive-Bayes, Bernoulli naive-Bayes. Now, for us, we have to use categorical naive-Bayes because all our variables are categorical, right? We have binary as well as multinomial. If all our variables are binary, then we will use Bernoulli naive-Bayes. So if all the variables are purely zeros and ones, then we use Bernoulli's naive-Bayes. But we have to use categorical naive-Bayes because categorically distributed data. All our independent variables are categorical variables. Okay. So we have to use this model, categorical NB. Try implementing it, categorical naive-Bayes. This is the model you have to implement on this particular data. If what you call multinomial naive-Bayes is also there, multinomially distributed, and is one of the two classic naive-Bayes used in text classification. Multinomial NB we predominantly used in text classification, where the dependent variable has more than 2 levels, like sentiment, positive sentiment, neutral sentiment, and negative sentiment. More than 2 are there. So multinomial NB there. So Gaussian, when most of your variables are what you call numerical in nature. So for this problem, we have to use categorical NB, categorical naive-Bayes. So try categorical NB for both, and then try to submit on the competition site. Otherwise, we'll do it in the next session. So any doubts? So you can now use iterative imputer in any of the problems where we have done manual imputations. Those places you can now use iterative imputer. Okay. So like HR analytics data, analytics with the HR analytics, Kaggle, house price prediction. So you can try working out with these. So mice in Python, it is called iterative imputer. Okay, when we do R, that time also we will be working with mice algorithm. It's very easy to implement in R. So that's what we have. So we have worked with the imputer, algorithm-based imputers, as well as the naive-Bayes. Theoretical part we have done. Next session we'll implement the models, and then we will see them. Okay. So you need to follow the what you call the model, and then check how the competition scores. It's not scoring, it is more about the process, how we have done. Now, you should be able to explain the mice algorithm. If you are implementing it, make sure if you're putting it in your GitHub, you have to explain the mice algorithm. Multivariate imputation using chained equations is the full form. The missing value variable will be treated as dependent variable, and you can use either classification model or numerical regression model based on the type of the variable, and then we will impute the model, impute the values with the predicted. Initial strategy has to be adopted because there should not be any missing values in dependent variable, right? So the missing value will be missing value variable will become the dependent variable. Rest of all will become independent variable. Okay, so that process repeats till all the missing value variables are imputed with the missing values. That we call it as mice algorithm, multivariate imputation using chained equations. Chained equations means multiple equations. Each kind of equation is linked to the like a chain, right? So link will be there for each of this. It's an algorithm-based imputation methodology, statistically model. It is a statistic model, and you can use any estimators. Okay, but we prefer tree-based estimators because they have good advantage in predicting the missing values compared to the logistic regression or linear regression. And moreover, tree-based models are for both binary as well as multinomial prediction. So if you simply you have to explain to them what mice is about and how it works, right? So let me see if I can find a diagram so that it will take a test. So this is the fill in missing values from random draws of non-missing data. For each iteration, for each variable v with missing values, optional subset data where v was originally non-missing, train model v tilde x, where x are the other variables in the data, do one of, replace missing values with predictions from the model, replace missing values using mean matching. If it is classification, predictions. Mean matching is, so this is the mice algorithm. Okay, so v tilde x means tilde is nothing but equivalent to where x are the other independent variables in the, so this is the mice